And during the course of my PhD, we were treating animals with insulin at one point of some experiments. And even though the animals were eating the exact same amount of food, the animals that were getting the insulin injections to be hyperinsulinemic were fatter than the other animals were. And that to me was impossible because I had been taught over my years that obesity was a matter purely a thermodynamic phenomenon, that if there's more calories coming in than out, then the animal would gain weight. I'm not saying that sentiment isn't true. I believe thermodynamics does matter. But if we try to understand thermodynamics in a living organism without the role of hormones like insulin, then we don't really evaluate all the variables. With polycystic ovary syndrome, one of the most common causes is the hyperinsulinemia. Insulin is known to have an effect on an enzyme called aromatase. And aromatase is this oft overlooked enzyme, but it's essential, particularly in female physiology, because within the ovaries, and to a lesser, much lesser degree in the testes, aromatase is the enzyme that converts testosterone into the estrogens. And so naturally, there's a lot of that happening in a female, particularly during her ovulatory cycle, where she has to have this really big spike in estrogens in order for ovulation to actually happen. But if the insulin is high, that's inhibiting the ovary's ability to flood the system with all these estrogens. And so her estrogens don't get high enough. And so she has ovaries that end up creating a lot of follicles, as happens every cycle. And rather than one of them popping out and ovulating, which tells all the other follicles to now go away back into nothing, we never have an actual ovulation because of the absence of the estrogen spike. So all of those follicles stick around in the ovary, making the ovary get bigger, and that's uncomfortable. And then the same thing can happen the next cycle and the next cycle. So again, to put a fine point on it, the elevated insulin prevents the estrogen spike, and the lack of an estrogen spike causes a lack of ovulation, and the lack of ovulation results in follicles that just don't know what to do. And they kind of linger around, making the ovaries get bigger and bigger, and ultimately contributing to PCOS, not to mention contributing to her infertility in particular, but not to mention the effects of the higher testosterone. Because if she's producing less estrogens, by default, she's producing more testosterone, and then that gives rise to some of the other more uncomfortable aspects of PCOS, if not the infertility that may be causing her acne, or maybe causing male pattern baldness, or top of the head baldness, and even more body hair, hirsutism, where she might have hair down her face or more coarse hair on her arms and legs. So that's even the most common forms of cancer, breast and prostate cancers, once again, each one reflective of the sexes. While the insulin resistance it's not likely that the insulin resistance is causing the problem. I wouldn't say that, but it's exacerbating the problem. It's amplifying it, where we know that insulin promotes cell growth. And in particular, prostate and breast tumors are known to overexpress insulin receptors. And so more insulin receptors means these are cells that can respond better to insulin's pro-growth signal. And when you combine that with the tendency of this person to always be eating starches and sugars, well, that's the fuel for cancer. Cancer cells use glucose 20 times higher than normal cells do. And so not only are we telling the cells to grow because of the high insulin, which is always present in insulin resistance, but then we're giving them all the fuel they need to grow by flooding the system with all that glucose. Yeah, well, it's not surprising, it shouldn't be, that if we are trying to understand a problem called insulin resistance, we probably should measure insulin. And that's where so many clinicians have been, well, I would say poorly educated. We only know what we've learned. And so it's not fair of me to expect everyone to know what I know, just like I don't know what anyone else would know. But yeah, with regards to insulin resistance, some tests that I would encourage any clinician to do, one would just be measuring fasting insulin. And if the fasting insulin levels are above 6 microunits per mil, that's a concern, or it's a reason to do the additional tests that I'll mention. One of the easier ones to do is the triglyceride to HDL ratio. And that is just triglycerides divided by HDL. And if that number is higher than around 1.5 or 2, and there's some differences across ethnicities, which is why we have to be a little more careful with that one. Just inherent differences. But nevertheless, if that number is higher than about 2, that's a red flag. Another one that's very, very predictive is the triglyceride glucose index. And this is one that just keeps I'm amazed at how many papers just keep coming out about this one. And it's a little more of a complicated formula, so anyone could look it up. But the nice thing about the triglyceride glucose index is that we always get those numbers. We always get glucose. We always get triglycerides, just like we always get HDL. So that other ratio I just mentioned is helpful. And then my favorite one, but it requires another atypical marker, which is free fatty acids. We don't normally measure free fatty acids. Now, you and I know this, but I just want to pause for just a second and just teach this, because I'm amazed at how many of my own students, university students who've gone through nutrient metabolism courses, they don't know the difference between free fatty acids and triglycerides. So the triglyceride number on the clinical test is the amount of the actual molecule. Well, it's kind of a ratio. It's a kind of an assumed number. The amount of this stored version of fat that is moving through the blood on lipoproteins like chylomicron or VLDL or LDL. That's how the triglycerides are carried. And it's a fraction of those that we rely on to give us the number of the triglycerides number. Free fatty acids are products of fat metabolism. That's when the fat cells are breaking down their triglycerides, taking these fatty acids, 3 of them that are linked together, and pulling them off one at a time through a process called lipolysis. And so free fatty acids are a reflection of the amount of fat that's being broken down from fat cells to be burned by the body normally. And what happens is this, which is one of the reasons I love it so much, because it's both reflective of nutrient metabolism and it brings the target on the fat cell, which I think is initially the most important cell in the progression towards insulin resistance. So when insulin is high, as you noted in the lectures you learned about, insulin will inhibit fat breakdown. It inhibits lipolysis. So if an individual is eating a bagel, for example, their insulin is high, their free fatty acids will be low. That's what you'd see. Now, give the person 6 or 7 hours, insulin's all gone, they're now in a fasted state, insulin will be down, and free fatty acids will start creeping up because there's this disinhibition of lipolysis. Now, in other words, lipolysis can operate freely. So these two should always be in opposites. If insulin's high, free fatty acids are down, or vice versa. However, when the fat cell has undergone significant hypertrophy, it's grown, and this was somewhat reflective of how I started this conversation, saying that when the fat cell gets big, it becomes pro-inflammatory. It becomes pro-inflammatory to actually try to correct a reduction in blood flow as the fat cells are too far from blood vessels. But at the same time, as the fat cell has swelled to about 10 times its normal volume, which is unlike any other cell in the body, no other cell is capable of that degree of hypertrophy in an adult. But at that point, the cell is getting so big that even though insulin keeps telling the fat cell to continue to grow, the fat cell stops listening and now starts leaking out fat. In other words, you now have a state where insulin is high, reflective of the insulin-resistant body, but now also free fatty acids are high, reflective of an insulin-resistant fat cell. But at that point, the cell is getting so big that even though insulin keeps telling the fat cell to continue to grow, the fat cell stops listening and now starts leaking out fat. In other words, you now have a state where insulin is high, reflective of the insulin-resistant body, but now also free fatty acids are high, reflective of an insulin-resistant fat cell. And if we appreciate the fact that the fat cell is probably the first cell to become insulin-resistant, that test becomes probably the most sensitive or earliest indicator, the canary in the metabolic coal mine, warning the clinician, hey, this person doesn't have insulin resistance based on all these other tests that Ben just mentioned. Even their insulin might be at a normal-ish number, but if it's a normal-ish number and high free fatty acids, that's a worry. And so the adipose IR index, which is what this is, will determine this. But it's interesting to note that there's differences. So anyone could look up this test, adipo-IR. But men and women, the sexes have different numbers here because women naturally undergo lipolysis at a significantly higher rate than men do. So women are naturally just burning fat at a slightly higher rate than men. So you take a healthy woman and a healthy man, her free fatty acid levels will naturally be higher than his. And so her ApoIR score naturally needs to be a little higher. So in women, the normal score is about 9. In men, the normal, well, that would be a warning if it's above 9, I should say. And in men, that number is much lower. It's about 5 because his free fatty acids should be lower. It's just one of the many differences, of course, between men and women, which are real. These are not the same sexes, not the same body type, but it's even reflected down to the very level of the biochemistry of the body and how the sexes use energy. So I would actually kind of put it in that order: fasting insulin, HOMA, and then all the others. If insulin is high, which it is in this insulin resistant state, you can't burn those fats. That's the problem. Normally, if free fatty acids are going up in the blood, it's because insulin is low, and so the body's burning the fat very readily.
Right.
Because as you noted, if insulin is low, fat burning is elevated. But with insulin being high, the body can't burn that fat. It has to store it. Another reason why I'm so fascinated by insulin is because, once again, insulin tells the body what to do with the energy that it has. And insulin abhors burning energy. It never wants to burn, it only wants to store.
When your insulin levels are always high, you're always in storage mode. And so, in between meals, when you're supposed to be able to tap into your own adipose tissue, into your own fat cells as fuel, your body's not letting you do that because your insulin levels are always high. So, soon after eating, you're hungry again because you can't tap into your fat in between meals. So, you're kind of
Yeah.
constantly in a storage mode and you can't tap into your stored fuels.
That's right. And it is documented. There are human studies to confirm everything you just said, including have groups of people eat 2 meals that are identical in calories, and the one that elicits the higher insulin spike will invariably lead to greater hunger sooner. In other words, the
Yep.
person gets hungrier sooner compared to the other meal, which had the same amount of calories but a more modest insulin spike. At the same time, another group, totally different lab, different study, found that when insulin spiked following a meal, the the energy availability, they called it, which was the sum of all nutrients available in the blood, the sum of ketones, lactate, fatty acids, triglycerides, anything that could be a source of fuel. When they looked at the levels in the blood, when insulin spiked, they were all down. It followed, which makes sense because insulin wants to
Right.
tuck everything away out of the blood. It wants to store it. And so what is in the blood goes down, and that becomes a particular problem for the brain, which, unlike muscle and liver and fat cells, has no storage depot. It doesn't, muscle and liver both have not only glycogen but also triglyceride pools. And of course the fat cells have enormous triglyceride pools. The brain doesn't. So the brain is constantly dependent on the amount of energy that's available in the blood. And so if the energy in the blood starts to go down, the brain is panicking because it doesn't have its own reserve of energy it can rely on, unlike the other tissues I just mentioned. And so it starts demanding that the body start eating, in other words, promoting a sense of hunger, even though the person has hundreds of thousands of calories stored on their body. But the brain doesn't know that. It only can sense what's in the blood. Restricting energy has merit, where you want the person to use their own energy and shrink those fat cells, thereby improving. There's less free fatty acids coming out, and now the fat cells are more insulin sensitive, and they're less pro-inflammatory, indeed even becoming anti-inflammatory. There's value in scrutinizing energy, but if low energy is the first step of this journey to improving metabolic health, then we put the patient in a very difficult position where they start to run out of energy in their blood. If the calories they are eating are insulin spiking calories, even though they're eating fewer calories, it would potentially cause the situation I just described, which is that the total amount of energy available, the nutrients available in the blood, drop, which starts pitting the patient against hunger. And hunger always wins. These strategies don't work long term. Not that the strategy itself doesn't have merit, but it shouldn't be the first step. The first step should be, how can I lower my insulin without making myself hungry all the time? Where if insulin is low, you learn how to use your own body's energy for fuel, your own fat cells for fuel. And the best way, you'd mentioned sort of 3 things. I believe there are 3 fundamental pillars, each reflective of one of the, or reflected in one of the macronutrients. So, firstly, the first way to help a patient reduce their insulin, thereby becoming more insulin sensitive and accelerating metabolic rate and losing weight more easily, is to control carbohydrates. Now, I'm not saying we don't eat any, and there are some nice ways to implement this idea or to put it into practice. And that is, don't get carbohydrates that come in bags and boxes with barcodes. Let your carbohydrates come as whole fruits and vegetables. You eat them, you don't drink them, and then you can enjoy them freely. You don't even need to count anything. Just let that be the first step. Control your carbohydrates, and that will help your insulin come down. But as you're restricting your carbohydrates and likely eating less, then at the same time, you want to make up for that so you're not hungry all the time. And so eat more protein and fat. So the next two rules: prioritize protein and don't fear fat. That one is important. It's easy to prioritize protein. We generally, culturally, we appreciate protein, although now more and more there's a fear of protein, which is very, very silly and not at all based in science. So get high quality protein, ideally from animal sources, frequently. At the same time, acknowledge that in nature, all of those high quality, best proteins for humans to eat come with fat. They are invariably connected in nature. That's how we should eat them. Don't fear the fat that comes with those proteins, and even be a little liberal with fat when it comes to butter, etc. Don't fear fat. And then, so if a patient incorporates those three ideas, that will help lower their insulin. And again, the body becomes more insulin sensitive. They're burning fat as a fuel more frequently, learning how to burn their own fat for fuel. And then once they've adjusted to that new routine and that new plateau that they've come to, then they can take that next step of, all right, I'm not quite where I want to get. I have more improvements and I know it. This has gotten me really far, but I want to go a little further. Now you can take that next step by starting to scrutinize total energy coming in a little bit. But not that you're counting calories. The best way to restrict energy, in my mind, is with structured fasting. And so that ends up being the kind of fourth part of this. Following, once you've learned how to manage your macronutrients, now learn to manage hunger signals and eating windows and being very disciplined. But as much as I'm an advocate of fasting, and I am, people need to know that how you end a fast is much more important than how long you fast. Too often, someone just shrugs their shoulders and decides to do a 24 or 36-hour fast, and they have no real plan in place, no structure for when they end their fast, what they're going to do. And so they end up just turning their fasts into these kind of glamorous versions of a binge purge cycle. They binge and because they're so hungry, they overeat and they are really uncomfortable. They are ashamed of what they did. Then they just resolve to do better the next day, and they just do the same thing again and again and again. So as much as I'm an advocate of fasting, it behooves all of us to pay a lot of attention to our habits, be honest, and have a plan for the fast. And it would be better to do a shorter fast and manage your eating at the end of that fast than do a longer fast and just kind of go crazy on eating anything you can get your hands on.